Hello and welcome to another video on Joe's Physics Corner. And today we're gonna have a go at simulating the double pendulum system. And you'll notice in the last few videos, the last 4 videos, the video that had 4 parts, I had a go at my first video on simulating a system, and we had a go at simulating a simple pendulum system. But today we're gonna take one step further on from that point and simulate the double pendulum system. But before we do that, we're gonna need some kind of mind map and also the theory in what we define and in how we're gonna define our variables. And in order to do that, we're gonna have to define some of the variables that we don't know. All right, so this part of the video is gonna be about the theory of the double pendulum system. All right, let's set up a double pendulum system over here. It's gonna look something like this, and this is going to be the origin, the pivot point. This is going to be the second pivot point, and we're going to have 2 kind of variables that decide what kind of state this system is at. And we're going to define this, and the 2 variables, the 2 only variables in the system is going to be θ1 over here and θ2 over here. Because these angles are basically what is changing in order to these 2 variables are the variables that are having an effect on the system and is basically changing the status of the system. And you could argue that, well, wouldn't the velocity of the balls of the masses change, and wouldn't the acceleration of the masses change? Yes, that's correct, but that is not the fundamental variable that is changing. The velocities of these objects are how these velocities are decided is based on the change in these 2 fundamental variables, and the effect of that would obviously be due to gravity. But these 2 variables are the fundamental variables that we're going to have to define by the order Lagrange equation. Before we do that, we're going to set up some constants. So I'm going to set the length of this string as L1, length of this string is L2, and the mass of this ball here is M1, and the mass of this one here is M2. Notice that I'm using the subscript 1 for this ball here, and the subscript 2 in order to define this ball here. And we could also set the coordinates of the center of masses of these points, of these masses, and that's going to be the x-coordinate of this point here is going to be L1 sine theta 1, comma, minus L1 cosine of theta 1, because you can see that the cosine is the adjacent side, which is how much it comes down, and because it's downward, we're setting the up part is positive and down is negative. We get minus L1 cosine theta 1, and sine because it's the opposite side. And this here is going to be the x-coordinate of this point is going to be this here plus this here, and so it's going to be L1 sine theta 1 plus L2 sine theta 2. And again, the reason why I put sine here is for the same reason, it's the opposite side, and also for the same reason we get the y-coordinate as L1 cosine of theta 1 minus L2 cosine of theta 2. Alright, we have our positions over here. And now we're gonna use the order Lagrange equation in order to define the equations of motion of the system over here. So first of all, we define the order Lagrange equation as the rate of change in L, or the rate of change in some variable, I'm going to say it's Q, is equal to minus d over d dt, the partial derivative of L over the partial derivative of some kind of variable to the time derivative, and we're going to set that as equal to 0. That is the Euler Lagrange. That's how Lagrangian mechanics is defined as. It is defined as any system that, in order to solve the equations of motion of a system, we have to implement this fundamental equation, which is applicable to any kind of system, any mechanical system, mechanical system. All right. Then so what we said we have our two variables. We had first variable we had is either 1, and the second variable, so this is going to be variables, as either 2. And we said here that this here, Q here, is our variable. And so what are the candidates, or what variables do we have to implement into Q as to get our final result? Well, it's going to be our two variables. So in Q, we're going to put in Q1 and Q2 by the time we know what L is. And we're going to use this to solve all of these other things in the future. But for now, we're going to have to solve what L is. And that's going to be a lengthy process. We know that L is equal to T, which is given as the kinetic energy, and the total kinetic energy of the system, I'm just going to say it's T, minus V, which is the potential energy. Notice that, be aware of the fact that these are all total values, so total of the system. Of system. All right, then if we have these two values, we're going to be able to solve this equation because we know what variables we're going to have to use. All right, so first step, we're going to solve what T is. What's going to be T? We said T is the total kinetic energy of the system. And that's defined as, well, the only kinetic energy, something has kinetic energy. For something to have kinetic energy, it's going to have mass and velocity. And in this system, the entities that have mass and velocity are going to be these two balls. And what do we know kinetic energy is equal to? We know that it's equal to 1/2 times mv squared. And so the total kinetic energy is going to be an addition of the kinetic energies of these two balls, which is going to be 1/2 m1 v1 squared plus 1/2 m2 v2 squared. We know m1, that it's a constant. We know m2, it's a constant. But we don't know v1 and v2. So we're going to find that out. So first of all, what is v1? Well, v1, v1. We're going to have to find what v1 is. But notice that because it's given as v1 squared, finding v1 squared is going to be much easier. And look at this equation. Look at this diagram over here. Let's say let's say this ball here at any point has a velocity of v1. What kind of properties? How could we divide this vector of called v1 into? Well, we can divide this into two perpendicular components. The first one's going to be vx1, and the second one's going to be vy1. And so we could say that v1 with this, by using the Pythagorean theorem, you could say that v1 squared is equal to vx1 squared plus vy1 squared. And what is vx1? Well, vx1 is basically the time derivative of the x distance, the displacement, how the distance from some point to the ball changes is going to be the velocity in terms of when we differentiate that in terms of time, we're going to have the velocity. So we could say that vx1, first of all, vx1 is going to be equal to, we're going to say that's x1 comma y1, and that's x2 comma y2, that's equal to these and these. So vx1 is basically the time derivative of x1. And for the same reason, vy1 is equal to the time derivative of y1. All right, let's look at Vx1 first. Vx1 is the time derivative of x1. So it's going to be d over dt of this over here. This is x1, L1 sine theta 1. That's going to be equal to, well, first of all, we do L1, sine becomes a cosine if you differentiate it, so cosine of theta 1, and we're going to have to apply the chain rule, and so we're going to differentiate the inside, and so we get theta 1 to the time derivative, and we write that as theta 1 dot, whereby dot basically means the time derivative. So Vx1 is theta 1 to the time derivative times L1 cosine theta 1, and for the same reason that y1 dot would be d over dt, this value over here, which is equal to minus L1, cosine becomes a minus sign, so minus sign, so it becomes a positive, and times the inside, so theta, again theta 1 dot. Just erase the plus here, it's, yeah. So we get this expression over here. And all right, so that's going to be Vy1. And so V1 squared, by plugging these two over here, we get this squared plus this squared. So let's just do that really quickly. Plus squared L1 squared sine squared theta 1. Now what do we notice here? Well, if we wrap these two expressions, these two expressions by theta 1 dot L1 squared, we get cosine squared theta 1 plus sine squared theta 1. And what do we know from trigonometric identities that this equals to? Well, this equals to 1. And so we get V1 squared is equal to theta 1 dot squared L1 squared. So we have our value for V1 squared. Just gonna erase all that. So we get the expression for V1 squared, which is equal to theta 1 squared dot theta 1 dot squared times L1 squared. All right, so that we know. So let's just erase this too and say that V1 squared is equal to theta 1 dot squared L1 squared. That's how we define V1. Now we have to do the same thing for V2. Now for V2 we do the same thing. We said V2 squared is equal to Vx2 squared plus Vy2 squared. And we know that Vx is equal to x2 dot, for the same reason we did here before, x2 dot, which is equal to d over dt of this whole expression. And we will get, I'm just going to do this really quickly. We do the chain rule, L1 cosine of theta 1, plus the chain rule again, L2 cosine of theta 2. Just make that really sure. And then, then Vx squared would be theta 1 dot squared L1 squared cosine squared theta 1 plus squared cosine squared theta 2. Now plus we times this and multiply it by 2. And so we get 2 theta 1 dot theta 2 dot L1 L2 cosine theta 1 cosine of theta 2. That's going to be our expression for Vx squared. And we're going to do the same for Vy squared. So Vy is going to be y2 to the dot, Vy2, forgot 2 here. And then that's going to be the time derivative of this expression over here. And so we notice that cosine, when we apply the chain, when we differentiate cosine, it becomes a minus sign. We have a minus already over here, so it becomes a positive. And so we get a very similar expression, but everything replaced with sign. So all the cosines are going to be replaced with signs. And so we get theta 1 dot L1 sine of theta 1 plus theta 1 dot theta 2 dot L2 cosine of theta 2. And we're going to have to going to be 2 here. By 2 to the squared, we get the square of the entire thing. So we do a very similar thing, but again replace everything by cosine, and so we get theta 2 dot squared L2 squared cosine squared theta 2 plus multiply 2, so 2 theta 1 dot theta 2 dot L1 L2, wait, sine cosine sine. Made a mistake over here, so these are all sines. So sine of theta 2, but this also becomes a sine of theta, sine square of theta 2. Yeah, so we get sine theta 1 sine of theta 2. All right, and it says that v2 squared is vx2 squared, so this expression over here, vx2 squared, plus this expression over here. You're going to have to add these two. All right, so vx2 squared plus vy2 squared, I'm going to erase this now. Vx2 squared plus vy2 squared is going to be equal to, and again, we're gonna shorten the process. So we see that cosine, it's the cosine here, cosine squared here, and sine squared here for the exactly same thing. And so we know that these two, when we add them together, we can group them with sine 1 dot squared and 1 squared times 1, because this plus this is equal to 1 due to trigonometric identities. And so we get theta 1 dot squared L1 squared, that's done. That's this part and this part done. And for the same reason, we could get this part done and this part done. And so we get plus theta 2 squared dot L2 squared. And then get all the other parts. So it's going to group with this expression over here and get this plus that. So cosine theta 1 theta 2, cosine theta 1, cosine theta 2 plus sine theta 1 sine theta 2. That's going to be our expression for vx squared plus vy squared. All right, so that is we know that here is equal to v2 squared. Okay, so we have this lengthy expression over here. Now we could erase all this part and get v1 is equal to that, and v2 is equal to this here. So v2 squared is equal to this long expression that goes like this. All right, so we get that. Okay. So now we could get t, right? T is basically 1/2 m1 times that plus 1/2 m2 times that. And so t is equal to 1/2 m1 times that is equal to z1 dot squared L1. And be really careful with these notations here, because you could get confused in, it's easy to get confused like during the process. So it's really sure to get these kind of things right. Plus 1/2 m2 times that, so theta 1 dot squared L1 squared plus 1/2 m2 again. So 1/2 theta 1 squared theta 2 dot squared L2 squared plus we get 2 and 2 canceled out, so m2 times L1 L2 m2 times the angles first. Plus m2 times theta 1 dot, theta 2 dot, L1, L2, cosine theta 1, cosine theta 2, plus sine of theta 1, sine of theta 2. That's going to be the entire expression simplified, like that. So T, our potential, no, our total kinetic energy of the system is going to be defined as this long expression that goes like this. All right, let's erase this and this too. So that's our value for T. We have a value for T over here. Now you have to do the same thing for V, the potential energy. Now the potential energy is a lot easier. The potential energy is just defined by the y coordinate, not the x. We don't have to care about the x because potential energy, it all depends on, we're talking about the gravitational potential energy here, but it doesn't really have to be. But in the system, we're only talking about the gravitational potential energy. And we know that it's only defined by the y coordinates. And by setting this part as the origin, so here height is equal to 0, we're going to apply basically mgh, EP is equal to mgh. All right, so we know that V, which is equal to the total EP total, is equal to mg times, I'd say y1, plus mg times, the mass, we know that it changes, so mass is not constant. Mass is constant, but it's different for these two objects, and so we get m1 gy1 plus m2 gy2. All right, m1 gy1 is basically minus m1 g L1 cosine of theta 1, and y2 is minus m2g L1 cosine theta 1 minus m2g L2 cosine of theta 2. And notice that I'm trying my best to expand all of them because it's going to be a lot easier if I expand when I'm going to have to deal with differentiating these expressions in terms of whatever theta prime, theta to the time derivative, theta dot, or just theta. It's going to be a lot easier. All right, so this is basically it for our potential energy. It's m1g y1 plus m2g y2, which we could express as this lengthy this lengthy expression over here. I'm just gonna check if it's right. M1g L1 cosine theta 1 L1 cosine minus mg m2g L1 cosine theta 1. Yeah, I think it looks all right. Yeah. So that's our value for V. So we have our V and our T, and so we now get what our value is for L. So L is the cool way of writing the Lagrangian. Is going to be equal to T minus V. So this here, 1/2 m1 theta dot 1 squared L1 squared plus 1/2 m2. I'm gonna not speak. Too much to say. Minus that, so it all changes to a positive. Alright, that's our long expression for our Lagrangian. Yeah, that's going to be right. Okay, so we have our Lagrangian. We're going to have this. Okay, that's going to be really important. That's our Lagrangian. And now if we, let's erase all this now. It has served its purpose now. Okay, bye. And now what we're going to do is solve this equation. So dl over the, what should you do first? What should you do first? I'm going to do theta 1 first. Because that's obviously theta 1 is theta 1. Theta 1 minus d over dt partial L partial theta 1 dot is equal to 0. Alright.